Hello everyone and welcome to Chapter 2. So our current theory on what an atom looks like is based on Dalton's atomic theory. In this theory, each element is composed of extremely small particles called atoms. And all atoms of a given element are identical to one another in their mass and their properties. But the atoms of one element are different from atoms of a different element. Atoms of an element are not changed into atoms of a different element by chemical reactions. Atoms are neither created nor destroyed in a chemical reaction. Compounds are formed when atoms of more than one element combine. A given compound always has the same relative number and kind of atoms. So this is Dalton's atomic theory, and what we base our current thinking on about what an atom actually looks like. So an atom is made up of subatomic particles. One is protons, 2 is neutrons, and 3 is electrons. And we typically show pictures like this where it kind of looks like planets revolving around a sun, kind of like a solar system, where in the middle here you have protons and neutrons, and then around the nucleus is the center where neutrons and protons are located. Floating around there is going to be your electrons. So these are your 3 subatomic particles, and we'll talk about these particles in detail. So they have a mass. Each one of those 3 different particles has a mass. A proton weighs 1.673 times 10 to the minus 24 grams. Now this minus 24 times 10 to the minus 24 indicates this is a very, very small mass. A neutron basically weighs the same, 1.675 times 10 to the minus 24th gram. So these are almost equal to each other in mass. And then electrons is 9.109 times 10 to the minus 28. And so that's actually way smaller than these two. So electrons are very small in comparison to the protons and neutrons located in the nucleus of the atom. They also have charges. A proton is going to have a 1.602 times 10 to the minus 19 coulombs. Neutrons have 0 charge, and electrons basically have the opposite charge. They have a negative 1.602 times 10 to the minus 19 coulombs. And coulombs are going to be our SI unit for electric current, which isn't critical at this point. Would be more important whenever you go to Chemistry 2. But what's important here is that neutrons have no charge, and then protons and electrons do have a certain charge, but they're actually opposite of each other, and so they can cancel out. Okay, so if we compare these on this chart, side by side, charge and mass, what we can do is simply say, relatively speaking, a proton and an electron, we can arbitrarily give, instead of having those large numbers in coulombs, we can just give it a charge of +1 for a proton, -1 for an electron, and then a 0 or neutral for neutrons. And then mass, we're going to, for now, measure masses in atomic mass units, which is going to be, which will change once we get into Chapter 3. But for now, we're going to measure in masses of AMUs, where protons and neutrons basically have the same mass in AMUs. And then electrons are much smaller. Okay, so this basically sums up the information from the previous 2 slides with respect to charge and to mass. So the take-home message here is that protons and electrons have opposite charges, where neutrons are neutral. And protons and neutrons have about the same mass. They weigh about the same, with electrons being much smaller in mass. And so for a typical atom, most of the mass is going to be contributed by the protons and neutrons because they're so much heavier. And electrons are going to be pretty much negligible with respect to the weight of the overall atom, the overall weight of the atom. So if we look at this picture, this is just kind of a diagram showing you, the 2-dimensional diagram showing an atom. In the middle is going to be your nucleus. And it contains the protons and neutrons. And then you have these electrons bouncing around, and they don't orbit like was shown on the previous slide. They actually will be here, and then they'll actually disappear, and then they'll show up somewhere else. And so they're basically randomly popping around the vicinity of that nucleus. And they're held onto that nucleus because they have a negative charge. If you remember what's in the nucleus, it's going to be protons and neutrons. So overall, protons and neutrons are going to have a positive charge, electrons being negative. So you basically have a positive charge here in the middle, and then these electrons have negative charges. And so this negative and positive, just like if you think about a magnet, are going to attract each other. And so the positive charge in the nucleus is actually holding those electrons on in the vicinity of the nucleus. Okay, and the atoms on a periodic table are going to be neutral, and that means the overall charge of this particular atom, you're going to have the same number of protons. So if we were talking about lithium, you'd have 3 protons and 3 electrons. It doesn't really matter where they are at this point, but if you have 3 negative charges, 3 positive charges, your overall charge, your net charge, is going to be 0. Okay, so when you look at a periodic table, it's going to be important in a minute, is that an atom in its normal state is going to have the same number of protons as it does electrons. That'll change when we talk about some exceptions, but for the most part, when you look at a periodic table and you can figure out the number of protons, you've also figured out the number of electrons. And that'll be important in just a minute. So we have 2 pieces of information when you look at a periodic table. Here I've taken lithium off the periodic table. It's number 3. It's over on the left-hand side. On this, you're going to see the name. You're going to see the symbol. But you're also going to see the atomic number, which is for lithium is 3. And what that tells you is the number of protons. What it also tells you is the number of electrons. It also tells you the identity of the element. So this is important. Any atom that has 3 protons is going to be a lithium atom, at least for this course. All right, so the number of protons tells you who you are if you are an atom. And these are arranged on the periodic table. All the different elements are arranged on the periodic table with respect to this top number, this atomic number. And so basically every element on the periodic table is arranged reading left to right, top to bottom, based on the number of protons that it has in this nucleus, which is its atomic number. Another number found on the periodic table is the mass number, also known as the atomic mass, and that's down here. So that's how much in AMUs, which is how we're measuring mass right now, atomic mass units. That's how many AMUs a lithium atom will weigh. And we'll talk about why this is a decimal number in just a little bit. And so this mass number is going to be the number of particles in the nucleus. And so here we have approximately 7 particles. And so some of those, for lithium, some of these 7 are going to be protons, and some of those are going to be neutrons, because this 7 is the sum of all of the protons and neutrons in its nucleus. And it's going to be approximately the overall mass of the atom, of that element, because the electrons really don't add much to the weight. Okay, so if you look at the periodic table, you'll notice you start up here on the left top corner with 1, which is hydrogen, and you basically read like a book. And what those are doing is, or how they're arranged, is the elements are arranged by their atomic number. And that number 1 tells you the atomic number. It also tells you the number of protons. It also tells you the number of electrons. What you can also notice about this is that as you move down the periodic table, if we just look at this row here, you notice that the atomic number goes up, which is the number of protons, but the mass also goes up. All right, we'll talk in detail about that later. Okay, so how do we determine the number of subatomic particles in an atom? Well, remember the atomic number, which is the number at the top of the element, is the number of protons. Okay, so if you look at the periodic table and you see the atomic number, you have figured out the number of protons. Well, what you've also figured out, since the number of protons equals the number of electrons, is the number of electrons as well. So if you look at the periodic table and you're looking at lithium and you see that the number at the top, the atomic number is 3, you have figured out the number of protons, which is 3. But you've also figured out the number of electrons, which is 3, because those are equal. All right, one way to remember this is that P and E rhyme, and so just remember the two that rhyme are the ones that are equal. Now the mass number, which is the number below the symbol at the bottom of that block, is going to be the number of neutrons plus the number of protons. And so if you need to calculate the number of neutrons, and you have the mass number from the periodic table, and the atomic number is the number of protons, you can simply take that mass number, which is neutrons and protons, right? So that's both of them combined. Subtract out the number of protons, and that will leave you with the number of neutrons. All right, so let's look at gold. Let's take that this example here that's highlighted in yellow. Okay, so here's gold. And what I want to do is go through how we can calculate the number of protons, electrons, and neutrons. Right? So let's do protons first. Well, the atomic number for gold is 79. We also said that represented the number of protons. So if the atomic number is 79 for gold, the number of protons for gold is also 79. If we look at electrons, well, our atomic number is 79, and then we know gold has 79 protons, and since number of protons equals the number of electrons, they're the same number, then there are also 79 electrons. So 79 protons, 79 electrons. And lastly, these neutrons. And neutrons are a little tricky, not tricky, trickier, because you have to use the mass number below, which is 197. And we're going to basically take 79 out of that 197 because that 197 represents protons plus neutrons. And so if 197 is our mass, and that's our protons plus neutrons, if we take out simply the number of protons, we can get our number of neutrons. So basically you take that mass, subtract the number of protons, so that's protons, that's mass, that's protons and neutrons, you'll get the number of neutrons. So there are 118 neutrons in a gold atom. So how do we get this? We took the mass, 197, subtract out 79, and that number leaves you with the number of neutrons. So here's a clicker question. It says, how many protons, electrons, and neutrons are there in an atom of cobalt weighing 59 AMU? All right, so we just round this number up to 59. And so we want protons, electrons, and neutrons. Well, for protons, you simply look at the mass number. It's 27. So there's 27 protons. And so that gets rid of E as an answer. And we have electrons. Well, remember, protons and electrons equal each other. So we're looking for something with 27 protons and 27 electrons. So that gets rid of C, because C has 59 electrons. And then our last three, A, B, and D, we need to now figure out neutrons to answer this question correctly. So what we're going to do is take 59, which is the mass number. We're going to subtract 27. That's a minus sign. What that's going to give us is a 2 right here and a 3 right here. And basically what we've done is this is the mass, which is the number of neutrons plus protons. We subtract out just the number of protons, and that leaves us with the number of neutrons. And so the answer here would be D. Okay, so unfortunately, by convention, whenever we write an element on a piece of paper, whoever decided this, actually, whoever started doing this, decided that we should actually flip the mass number and the atomic number. So on the periodic table, what you'll see is the atomic number up top and the mass number below. But when we write an element, for example, boron, we actually flip these two, where this is now our atomic number and this is our atomic mass. So that's opposite of what you'll see on a periodic table. So just keep that in mind. And so what this is telling us is that there are 5 protons and 5 electrons in boron, and there are 6 neutrons. Okay, we're going to talk about isotopes, but before we do, we're going to talk about birds. And I know this might sound silly, but hopefully it gets the point across. I've actually never used this analogy, so we'll see what happens. So let's say that I sit outside in my yard all day long and I count birds, how many birds I see. And let's say I only see 3 types of birds. We have a sparrow, a crow, and a hummingbird. And importantly, each one of these birds has a corresponding weight. And we'll just do weights in pounds right now. And so, but what's important is they're all birds. There are different types of animals, but these are specifically birds. And so if I sit outside all day and I just calculate the percentage of birds that I see, let's say on this day I saw 95% birds, sparrows. I only see 4.9% of the birds were crows, and then 0.1% were hummingbirds. So I see less hummingbirds than I do sparrows, and I see less crows than I do sparrows. Sparrows are basically everywhere. But let's say that for some weird reason, I'm really interested in the weights of birds. And each one of these sparrows weighs half a pound. Each one of these crows weighs 2 pounds. Each hummingbird weighs 0.1 pound. But what I want to know is basically, if I were to add up all the weights of all the birds that I saw, I want to know the contribution of that overall weight by sparrows, by crows, and by hummingbirds. Well, of all the birds that we're looking at, 95% were sparrows, and they weighed half a pound each, and so the percent contribution of weight of all the birds I saw mostly comes from sparrows. Some of the weight, the overall weight of all the birds combined, would come from crows, and very little would actually come from hummingbirds. So remember, these are all birds, and so now we're going to talk about elements. And so let's say that, for example, hydrogen could come in different flavors. Maybe a type of hydrogen that has a middle type of weight, a very heavy weight, and then a very light weight. But all hydrogen, they just come in different weights. And so when we talk about the overall mass of hydrogen, we have to take into account all 3 types of hydrogen. And that's what's going to be on the next slide. Here's hydrogen, and there's 3 different versions. And now this is the atomic number, 1, and that tells you who you are. If your atomic number is 1, you are hydrogen. And so in this first version, we have 1 proton, 1 electron. There's actually no neutrons. Here we have hydrogen with 1 proton, 1 electron, and 1 neutron. And you see this number 2 up here, that's actually the protons and the neutrons. This number 1 over here is going to be your protons and your neutrons. And then this hydrogen, this flavor of hydrogen, actually has a mass of 3. It actually has 1 proton, but it has 2 neutrons. And so these are called isotopes of each other. And each isotope is the same element. They just vary in the number of neutrons. And so here we have 3 different versions of hydrogen that have different weights. And the different weights, or the different masses, are going to be a result of more or less neutrons in the nucleus. Okay, now that I look back on the bird analogy, maybe it didn't make much sense, but these are isotopes. They're the same element, they just vary in mass. How do they vary in mass? They vary in the number of neutrons. And there's some animations in it. Okay, so if we look at this periodic table, and let's look at hydrogen again, and we look at this mass, which I'll rewrite up here so you can see it more clearly. This mass is almost 1, but it's a little bit heavier than 1. Well, that mass is actually going to be an average of the 3 isotopes that we saw on the last page. Remember, there's 3 different flavors. They have different masses. When we add them together and divide by 3, we get this average atomic mass. Now, this not only depends on the weight of each one of those isotopes, but it also depends on the relative abundance. And so since this number is very close to 1, and not very close to 2, and definitely not close to 3, which are the masses of the latter 2 hydrogen isotopes, what that means is that the first isotope on the previous slide is actually the most abundant. And we only have a little bit of those other 2 isotopes floating around in nature. But they're all hydrogen. And so if we just take all those 3 different versions and their percent abundance in nature and average them together, we get this mass. And that's why all of these masses have a decimal sign, because they're actually all averages. They're average masses. That's what we call it, average atomic mass. So they depend on the number of isotopes present. They depend on the relative abundance of each isotope. And they depend on the atomic mass of each one of those isotopes. And so to get this, to calculate an average atomic mass, we take the sum of each one of those isotopes. And the sum that we're going to be adding together is the mass in AMU and the abundance. And the abundance are going to be in percentages. Let's say something is 60%. Well, remember, to turn a percent into a decimal, we want decimals for this calculation, so we need decimals. You're actually going to have to divide by 100. If you divide 60 by 100, what you get is 0.60. All right. Another way to do that is take that percent sign and pretend like there's a decimal there and just move it over 2 places. It's the same thing as dividing by 100. Okay, so make sure you express the percentage in a decimal. So you'll always be given a mass for each one of the isotopes and a percent abundance. And make sure that those percents go into a decimal form. Okay, so I've rewritten it on this slide. And we're going to look at this particular example. It says chlorine naturally occurs in nature in 2 different forms. All right, so there's only 2 isotopes for chlorine, at least for this example. So chlorine exists in 2 different flavors. Right, here's this one that has a mass of 34.969, which is approximately 35, so we call that chlorine 35. And then chlorine 37, which a specific mass is 36.966 AMU. And then in front of that is going to be the percentage. So these are the percents of each one of those in nature. So this is kind of becoming a mess. Let's erase some of this. Okay, so chlorine 35, what this information is telling you is that 75.78% of all the chlorine is chlorine 35. And here's the mass of that particular chlorine isotope. The rest, 24.22% of chlorine, is going to be chlorine 37, which has this particular mass. So these 2 isotopes have different masses, and they exist in nature at different abundances, different percentages. So what is the average atomic mass? What is the mass that's going to be reported on the periodic table? Well, it's basically going to be an average of these 2. We will take into consider the mass, but we'll also take into consideration how abundant each one of those is. And then we'll just basically get an average of those 2, and we'll call that the mass of chlorine. So here's the calculation worked out from the previous slide. It's that same calculation, although I've extended the actual calculation in a little more specific manner. So what we're going to do is we're going to take our question, which is here, and I'm going to call this first chlorine 35 isotope number 1, and chlorine 37 is going to be isotope number 2. Now we have to use the masses for each one of these, as well as the percentages put into a decimal form for each one of these. And so we're going to look at, we're going to take the information for isotope number 1 and plug it into here. And then we're going to add that to the information for isotope number 2. Now importantly, chlorine has two isotopes that we're working with, but sometimes you have elements like we saw with hydrogen that have 3 isotopes, or some even have 4 isotopes. What you would do if you had 3 is you would do the same thing. You would just add another addition sign, put the mass for isotope number 3 times the abundance for number 3. And if you had 4, you would just do this again with the same information. But here we only have 2. So we're only worried about adding 2 numbers together. And how we get those numbers is we plug those into this calculation. All right, so the first thing we'll do is we'll take isotope number 1 and put the information into this equation. Here is the mass that is directly taken from the question, 34.969. And here is our percentage turned into a decimal form. So we move that decimal over 2 places, the same thing as dividing by 100, and we get 0.7578. So information for our first isotope is in the bag, ready to go, ready to be calculated. And then we add the same information for isotope number 2. So we take this mass for isotope number 2, put it into the calculation, take our percentage here, and move that decimal over 2 places to get 0.2422. Now for orders of operation, we're going to multiply before we add. So we're going to multiply our numbers together that are in parentheses. So we'll multiply these together, and we come out with 26.50 AMU. We're going to multiply these together. We're going to get 8.953 AMU. Once we're done with that, we can then go back to the addition and add these 2 numbers together, and you get 35.45 AMU. And that is going to be the average atomic mass for chlorine. If you look at the periodic table, you're going to see a number very close to this. It might depend on the periodic table. It might be off by a hundredth of a point or something, but be very close. And so the number that's represented on the periodic table is going to be the average of the different isotopes with respect to their mass, but also with respect to how abundant they are in nature. Okay, so for this slide, let's just ask a question. Which of the pairs are isotopes of the same element? All right, so first of all, at the bottom, you have your atomic number, which is, remember, opposite of what we see on the periodic table when we write these on a page. And up top, we're going to have our mass. Now remember, isotopes are the same element, they just vary in their mass. And so what we're looking for is 2 elements that have, one of these is going to have the same number of protons, because protons tell you who you are. Well, how do you know how many protons there are? That's the same number as the atomic number. So if we look at these 3 examples, A, B, and C, only B has the same number of protons for both of these versions of whatever element X is. And they vary in the mass. And so that means these are the same element. They just vary in their mass, which is a variation in their neutrons, because that's what isotopes are. They're the same element. It's just their mass is different because they have different number of neutrons in their nucleus. So the answer here would be B. These are isotopes of each other. So if you get asked a question on an exam like this, just make sure if you're looking for isotopes, you are looking for something that has the same atomic number. And when we write elements, we take them off the periodic table and write them on a piece of page. It's always these lower numbers, right? So these would be different elements. 7 and 8, those are different elements. 8 and 7 are different elements. But 6 and 6, same element. Their mass varies, therefore those are isotopes of each other. The answer is B. Okay, so isotopes are elements, atoms of the same element that vary in neutrons. Ions are going to be atoms of the same element that vary in electrons. And they're going to have a charge. Now remember, in an atom on a periodic table, for example, if this is an atom in the nucleus, let's say we have 2 protons, we're going to have 2 electrons to neutralize those 2 protons. Now with ions, what happens is we lose electrons or we gain electrons. And when we do that, we basically shift the charge, because on a normal atom with 2 protons and 2 electrons, those neutralize each other. If we add another electron in the mix, now we actually have a negatively charged atom. Now if we take away electrons, now we have a positively charged atom. And so ions are going to be atoms of the same element that just vary in charge. And this is because they vary in the number of electrons. So for ions, we're not losing or gaining positive charges. The positive charges stay the same. Those are the protons. What we're doing is gaining or losing electrons, and that's going to shift the charge from neutral to either positive or negative. We have 2 types, cations. Those are going to be whenever you have an atom with a positive charge. And they have more protons than electrons. Anions are going to be negatively charged. They have more electrons than they do protons. And one way to keep these straight is cations we're saying cations have a positive charge, which we represent with the plus sign, anions with the negative sign. Well, if you look at cations, it actually, if you think about it, the letter T actually looks like a plus sign. So if you're trying to figure out a way to keep these straight, which one's positive, which one's negative, well, I'll just look for that big plus sign sitting right there in the word. But do what you want. Okay, let's look at an example. And for this example, we're actually going to calculate the number of protons, electrons, and neutrons. Here we have a neutral. This is a neutral atom. And then here we're going to have an ion. And the charge is always going to be put in this vicinity here, the top right quadrant. And so since nothing is written here on the left-hand example, we say that's a neutral atom, and we just have an understood 0 right there. It's only when we have to write a negative or positive that does a number actually show up, like over here. Okay, so this is going to be our atomic number. Remember, if you're looking at a periodic table, these two are going to be flip-flopped. All right, so keep that in mind. When we write them on a page, we put the atomic number underneath. So this tells you the number of protons. Okay, now if this atom is neutral, that means that the number of protons, which is 6, equals the number of electrons. And then how do we get number of neutrons? We're going to take the mass, 14, we're going to subtract 6, and we'll get 8 neutrons, which we've already covered. Okay, let's go ahead and move over here to the right-hand side to our ion. Now our ion has this -4, and remember, ions vary in the number of electrons. Electrons have negative charges. What this -4 means is this atom actually has 4 extra electrons added onto it. So when you see carbon with a -4 charge, what that means is electrons have been added, which is counterintuitive, but for chemistry purposes, when you see a -4, that means 4 electrons are added. When you see a +4, that means 4 electrons have been taken away, which is opposite of all your experience in your life. When you see a negative on there, you would think, oh, they've been taken away, but it's opposite. The reason is because 4 electrons with a negative charge have been added and therefore given us a -4 charge. So let's do the calculation. Protons. Well, atomic number tells us protons. And this is where ions are going to differ. When we get to electrons, what we're going to do is we're going to say, well, we know there's 6 electrons because protons and electrons equal each other, but then we need to add these 4 extra ones. So 6 plus 4 will give us 10. In this case, 14 minus 6 has not changed to get the number of neutrons, and so we still have 8 neutrons. And so if you look at this slide, the only thing that has changed between these two is going to be your number of electrons. Let's do another example. This example, we're looking at sodium. Sodium has an atomic number of 11. What does that mean? Well, if there is no charge up here, it's neutral, and therefore the number of electrons and protons equal each other. We know that if atomic number is 11, we have 11 protons, and we have 11 electrons. And then if we take 23 and subtract 11, we wind up with 12 neutrons. Now if we look at sodium with a +1 charge, it's still sodium, so it's still going to have 11 protons. But when it comes to electrons, we're going to take our known 11 electrons, and this means we have lost an electron. The +1 means you've lost a negative charge. So we're going to take 11, and we're actually going to subtract 1 to get 10 electrons. And the neutrons hasn't changed. So when you look at this example, the only thing that really has changed is the number of electrons, because these are ions of each other. How do we know they're ions of each other? Because we can look up here and say, well, that one's neutral, this has a +1, so this has lost an electron, minus electron. And so we'll just take 1 away. Okay, so isotopes, just to compare isotopes versus ions, isotopes, remember, vary in the number of neutrons, and that'll change their mass. Ions are going to vary in their number of electrons, and that's going to change their charge, but it doesn't change their mass, and the reason is because electrons weigh almost nothing, so you will never see the mass change, you'll just see the charge change with ions. We have 2 flavors, we have plus and minus. These are cations and these are anions. So if we look at this question, revisit cobalt, but now we're saying that we have a +2 charge on cobalt. And it's asking for a number of protons, electrons, and neutrons. Okay, so let's do protons first. Protons, bam, that number right there. Now remember, what I should mention is this picture is taken from a periodic table. Periodic table, atomic numbers up top, mass below. If you see this written on a piece of paper, it's going to look like this, with 59 up top, which I'm rounding that number, 27 down here, and a +2 here. Okay, so if we look at, let's go ahead and just use, I guess, this version here. This is going to be our atomic number 27, so that tells us number of protons. All right, so it's not going to be either one of these. This also tells us the number of electrons, but this means we have to subtract 2 because this ion of cobalt has lost 2, so we're looking for something with 25 electrons. All right, so even right now we can go ahead and eliminate these 2 options, and this would be our answer. And how do we get neutrons? Simply take that 59, subtract 27, and you're going to get your 32 neutrons. But the point here is calculating the number of electrons from an ion. This is a +2 cobalt ion. Okay, now we're going to talk about the periodic table, and specifically how it's laid out and what the different parts are called. We have groups, sometimes called families, groups and periods. We've already talked in chapter 1 about nonmetals, metals, and metalloids, and then we're going to talk about these other alkali metals, alkaline earth metals, chalcogens, halogens, noble gases, transition metals. So here's the periodic table. Groups are going to be our columns. Periods are going to be our rows. We have metals that are this color, right? So most of the periodic table are metals. Non-metals, which are in blue. Metalloids, which you don't talk too much about. And specifically, if we go to the last part of that list, we have our first group called alkali metals. Second group is alkaline earth metals. Move over, we have chalcogens, halogens or halogens, I say halogens, and noble gases. And then here in the middle, we have our transition metals. So you'll need to know what these are. For example, if it said, what group is sulfur in? You would say, oh, that's a chalcogen. Right? Groups are going to be your up and down rows, up and down columns. Sodium, for example, would be an alkali metal. Neon would be a noble gas. So the question is, what is bromine? How would you classify that? Well, if you look at the periodic table, it's going to be in the second to last column on the right-hand side, and those are going to be your halogens. Okay, now we're going to discuss types of formulas. We have molecular formulas, something called empirical formulas, and then we have structural formulas, and they vary with respect to how much information they tell us about a certain compound. Remember, compounds are when more than one element, type of element come together to form a group that are bound to each other. So molecular formulas provide the elements present. So a molecular formula will tell you what elements are there, and it tells you the actual number of each one of those elements that's in the compound. Okay, so here's an example. C6H12O6. It tells us there are 6 carbon atoms, there are 12 hydrogen atoms, and 6 oxygen atoms. So it tells us not only the elements that are there, which are carbon, hydrogen, and oxygen, but it also tells us the number that's present, and that's that subscript number that you see behind. All right, so basically there are 6 carbon atoms here in this compound, there are 12 hydrogens, and there are 6 oxygens. And so this is a molecular formula. Specifically, the molecular formula is C6H12O6. That's our molecular formula. An empirical formula does tell you which elements are there, but it just gives you relative numbers of each one. So for example, CH2O, what that's telling you is that there is twice as many hydrogens as there are carbons, and twice as many hydrogens as there are oxygen. Well, if you take, let me rewrite that. If you were to take C6H12O6, you can see also from the molecular formula, this is just from the last page, that there are twice as many hydrogens as there are carbons and oxygens. And so what an empirical formula is telling you is just the relative ratios. And it's actually a reduced version of this. If you were to take these subscripts, 6, 12, and 6, and reduce them, you can divide them all basically by 6. So we can divide by 6, divide by 6, divide by 6. You would get CH2, because 12 divided by 6 is 2, which is going to be your empirical formula, EF. Okay, so a molecular formula tells you the elements present and how many there are. Empirical formula tells you elements present and just the relative ratio of how many there are to each other. Now, a structural formula gives you a lot more information. It provides what elements are present. It also tells you the actual number, just like a molecular formula, but it also tells you how they are connected. So for example, this is C6H12O6. But what you see here is these lines, and these lines are bonds. And so structural formulas tell you how these are actually connected to each other. So there's a lot more information here in a structural formula than there is in a molecular formula, and especially than there is in an empirical formula. And we will get to these particular lines because these are bonds, and that'll be a later chapter. So clicker question, which one of the formulas is an empirical formula? And so if you're asked a question like this, what you need to do is you need to look at the subscripts down here, which are below, and you need to ask yourself for each one of these, the question says which one of the following formulas is an empirical formula. So we're looking for something that cannot be further reduced. Well, if you look at this one, we could actually divide all of those subscripts by 2 to get a reduced version. If we did that, we would get CH3O. So that's not an empirical formula because it's not its most reduced version. We could also divide this by 2, letter C. If we do that, we would get CH3 for our empirical formula. We've already talked about this one. Divide that by 6. You get CH2O. This one, you can divide both of those by 5 to get a reduced version, to get CH. But if you look up here at A, which is actually the answer, if you take 3, 6, and 1, the only thing you can really divide by is 1. And if you do that, you wind up with just simply this answer. So this is actually in its most reduced form. You can't take those subscripts and divide by anything evenly. And so that will be your empirical formula. Okay, now we're going to switch directions completely, and we're going to talk about nomenclature. And this is how we name compounds. What we're going to do is we're going to first discuss charges for elements. Okay, we need to look back at the periodic table, and I'm going to show you some trends from that periodic table as to what the charges are for elements if they do become an ion. We're also going to classify, number 2, classify compound as either ionic or molecular. Number 3, we're going to see how to name molecular compounds. Number 4, we're going to see how to name ionic compounds. And so naming molecular compounds is actually pretty straightforward. There's a lot of work to do with ionic compounds, unfortunately. Then we're going to discuss how we name polyatomic anions and cations, and we'll discuss what a polyatomic is. And then we'll learn to write formulas from given elements or write elements from a given compound. Okay, so first we'll discuss charges for elements. Okay, one thing we have to get clear before we go into the charges is the difference between a metal and a non-metal. So you guys have to know where this stops. So metals are going to be on the left-hand side, and hydrogen is kind of weird. It can be, sometimes you'll see hydrogen where it is, located here. Some periodic tables, you might actually see hydrogen over here. And many times you might actually see helium moved over here. And so we'll go over details, those details later when we get to that point. So these are metals. These are non-metals, and that's going to be important, okay? Because when we talk about ionic compounds, an ionic compound is going to be when you take a metal and combine it with a non-metal. A molecular compound is whenever you take 2 or more non-metals and add those together. We'll get into that in just a little bit. But just recall from chapter 1 that the left-hand side over here are going to be metals, and the right-hand side over here in blue are going to be your non-metals. Now let's talk about charges. Here's a periodic table. Whenever an atom has a charge, they will have a specific charge. Right? Remember, these are metals on this side, and then over here it's going to be our non-metals. What you should notice about the metals is they all have a positive charge. Metals form cations. Cations are going to be elements with a positive charge. Metals typically form cations. Cations are just a term for a positively charged atom. And what you should notice from this periodic table is that all these nonmetals over here actually have negative charges. So nonmetals typically form anions. Okay, and so if you look at this first group, group 1, if you notice, all of these, hydrogen, lithium, sodium, potassium, so forth, all have this +1 charge. All right, and we don't write a +1, we just put plus, and we have an understood 1 there. All right, so there's actually, for if we look at hydrogen, there's an understood 1 there. For lithium, there's an understood 1 there. Sodium, understood 1. Now look at group 2. Group 2 always forms a +2 charge. So all of these in this column have a +2. Group 3, which is actually considered group 3b, all has a +3 charge. The truth is we really don't talk about this group very often. What I would do is focus on first group +1, second group +2, and then here in the middle we go to transition metals. And the ones that are highlighted in yellow are the ones that you need to know are what we call variable charge metals. And that means they can form a cation. For example, if we look at iron, iron can form a +2 cation or a +3 cation. Now you don't need to memorize +2 or +3. You just need to know everything in yellow, all these elements, manganese, iron, cobalt, so forth. Those are variable charge metals. Don't memorize the actual charges, just know they can form different charges because that'll be important later. Okay, and if we move along this way, you see starting with nitrogen, this column is going to have a -3 charge. And you can ignore these guys down here. The next column over, starting with oxygen, are all going to have a -2. There's -2, -2, -2, so forth. And then this column here is going to have a -1 charge. And then the noble gases at the very end are going to have 0 charge, and they have no charge. Right? And those actually don't like to react. And we'll talk about why that is and how that 0 charge is related to non-reactivity later in this course. So let's get rid of some of the mess. And I'm going to just mention that you should know that for first and second column, +1 and +2. Starting with nitrogen going this way, -3, -2, -1, 0. And then we have some variable charge in the middle. Remember, don't memorize these charges like for nickel. Just know that nickel is one of these that can form multiple charges because that'll be important whenever we look at compounds containing nickel or copper or iron or so forth. Okay, so we needed to visit that, and you need to know those different charges that I have circled. Okay, so we did a little bit of discussion. Now we're going to really talk about nomenclature. We're going to classify compounds as ionic or molecular compounds, and then we'll discuss how we actually name those. Okay, so let's look at ionic compounds. Ionic compounds are going to be a compound composed of a metal, of metals, and non-metals. So if I look at, just draw a generic periodic table that looks like something like this, with my line going across, these are non-metals, these being metals. An ionic compound is going to take one or more of these and combine them with one or more of these. And that's going to be an ionic compound. So for example, if I drew sodium chloride, and if you looked where those are, relatively speaking, sodium is going to be over here, a metal. Chlorine is going to be over here, a non-metal. And so this would, sodium chloride would be an ionic compound. And another name for ionic compound is actually a salt. There are different types of salt. Table salt is actually this ionic compound of sodium chloride. Molecular compounds are going to be only composed of nonmetals. And so they're not going to have any metals in them. They're strictly going to combine things over here. So for example, we have carbon and oxygen are two elements over here. An example maybe would be CO2, non-metal, non-metal, therefore molecular compound. So hopefully that makes sense. So let's see how to name these things. And we're actually going to start with molecular compounds because those are easier. So just before we get to naming molecular compounds, let's just make sure that we are clear and we can classify some of these compounds either as ionic or molecular. Right, if we look at water, water is going to be molecular, and that one's tricky because if you do look at the periodic table, hydrogen is usually listed right here. But in this course, you can consider moving hydrogen over in the non-metal section. So water would be a molecular compound because oxygen and hydrogen will both be over here on this side. Two nonmetals, molecular. Sodium chloride would be ionic. I just gave that example. Hydrochloric acid, hydrogen, and chlorine is over here as well. So that would be molecular. Carbon, hydrogen, oxygen, all in this area. That would be molecular. Iron chloride, iron is over here in the transition metals. That's supposed to be an Fe. Chlorine is going to be over here on this side of that stair step, and so that FeCl combined is going to be ionic. All right, so this is if we just go back down the list, this is two nonmetals, molecular. Metal, nonmetal, ionic. Two nonmetals, molecular. Bunch of nonmetals, molecular. This is going to be metals and nonmetals, ionic. Okay, so let's see how to name these molecular compounds. So molecular compounds contain only nonmetals. All right, that's what we're focusing on, not ionic compounds right now. Focusing on molecular compounds. So we use prefixes, and these are Greek prefixes, to describe the number of atoms of each element present in the compound. So mono is 1, di is 2, tri 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, or nona, deca 10. Importantly, if we're naming a compound, like carbon, CO2. We know this is carbon, we know this is oxygen, but this is carbon dioxide. All right, so we importantly, we don't call it mono carbon dioxide. The reason is because you never use mono for the first element in a compound, and that's the first element. If there's only one, which there is because there's no subscript here, so there's an understood one, you just call it carbon. You don't use mono. And then for the second or the last element in here, we use an IDE ending. All right. Also, we have two oxygens. All right. So this is going to be carbon. So we don't use mono. So carbon. That's supposed to say carbon. There we go. And we have two oxygens, so we're going to use the prefix di. You almost always use those prefixes unless it's the first element that only has one. And then typically what you do is you take the first syllable of the second element, which would be ox. Oxygen has 3 syllables. First syllable is ox, and you add IDE to the end. There's IDE. So this is carbon dioxide. And ide is indicative that this is a compound. Here's some other examples. We just did carbon dioxide. This is 2 chlorines, 7 oxygens. Now, for this first example, there was only 1 carbon, so we didn't use mono. But here, in this next example, we have 2 chlorines, so we're going to say dichlorine, and then we have 7 oxygens. We're going to say hept. There's your first syllable, ox, and then IDE ending. Next is nitrogen monoxide. There's only 1 nitrogen, so we don't say mono, we just say nitrogen. and then there's one oxygen. And since this oxygen is not the first element in this compound, we do give it mono, so it's monoxide. Oh, monoxide. All right, here we have disulfur dichloride. Notice all of these have an IDE ending. That's how you know that is a compound. So that's it for naming molecular compounds. It's pretty straightforward. You just need to know the Greek prefixes. Remember, never put mono on the first element, and then the IDE ending has to be on the second element. Now we're going to move on to ionic compounds. We're going to name ionic compounds. So not talking about molecular, now we're focusing on ionic compounds, and those are going to be metal, a compound that contains a metal and a non-metal. Okay, so when you name an ionic compound, again, ionic compounds are made from metals and nonmetals. That metal is typically written first in the name, and the nonmetals are usually written after that. You're going to look at that metal, and you say, do I know the charge of that metal? Is it a fixed charge? Well, fixed charge means that they're in a column that the charge never changes, right? That would be group 1, always a +1. Group 2, always a +2. Or is it aluminum, which is a +3? If the answer is yes, what you're going to do is name the metal. Just name it. And then you name the nonmetal. And the nonmetal is going to get the IDE ending. So for ionic compounds, we don't use the Greek prefixes. Those are for molecular compounds. Here, if you're working with a group 1, if your compound is a group 1 metal, contains a group 1 metal, or a group 2 metal, or aluminum, you're simply going to name the metal, and then name the nonmetal, and just make sure the nonmetal gets the IDE ending. Here's some examples. Sodium chloride. Well, this is in group 1, so we know it's fixed charge, always +1 charge. So group 1 is fixed, so we just name the metal sodium. And then we're going to name the nonmetal, chlorine. We're just going to take the first syllable of chlorine and add IDE at the end. Let's look at the next one. Potassium, bromide. Potassium is in a fixed group. So we just name the metal. Then we take the first syllable of the nonmetal, add IDE. Lithium, lithium iodide. Lithium is a fixed group, so we name the metal. First syllable, kind of iodine. It does include the D with the IDE ending. Calcium, it's in group 2. It's a fixed charge metal. So we're going to name the metal, name the nonmetal, first syllable, add IDE. Magnesium, it's in group 2, always a fixed charge, +2. Name the metal, first syllable of the nonmetal, IDE ending. We don't use Greek prefixes for ionic compounds, just for molecular compounds. If you notice, how do I know these are ionic compounds? Well, just to refresh from the previous slide, ionic compounds are always a metal plus a non-metal. If you look at sodium chloride, there's your metal, there's your non-metal, and it's going to be the same for all of these on this list. Okay, so let's see what the answer to this question is. The name of this compound, Na2O, is, well, this is fixed charge, so we're just going to name that metal, sodium. And then we have oxygen, so we're going to put the first syllable and add IDE. All right, so this should be sodium oxide, which is D. Now, another scenario is when you look at a compound and then you know it's ionic because there's a metal and a nonmetal. And let's just say that you look at that metal and you say, no, it's not in group 1, no, it's not in group 2, it's not aluminum, it's probably one of those metals, for example, that's a transition metal that's a variable charge that can make different plus charges. If the answer is no, it's not, the metal is not one of those, you're actually going to have to do something a little different. It's very simple. You name the metal just like before, but then you have to designate the charge of that metal. You don't have to memorize those from the periodic table. It'll actually be given to you in the formula for the compound. You're going to put the charge of that metal in Roman numerals in parentheses. Roman numerals in parentheses. So basically you'll name the metal just like before, just like if it were a fixed charge metal. But then we just have to say, okay, that was a +2 metal, and then you just name the non-metal with the IDE ending, just like before. So here's some examples. Iron chloride. So there's iron and 2 chlorines. Well, if you look back at the periodic table, iron can form different charges. So we know it's positive because it's a metal and they form cations. And let's just not put the value in here yet. But chlorine is always a -1. Now if I have 2 chlorines, and which I haven't mentioned yet, if you look at this compound, all compounds are neutral. There's no charge on a compound, so it's neutral. Well, if I have 2 chlorines, that means there's a -2 from those chlorines. So if these need to equal 0, what does my charge need to be for this iron? Well, the answer is a +2, because a +2 -2 will equal 0, and this is going to be the charge of the compound. So so when we're naming an ionic compound with a metal that has a variable charge, you know that variable charge because it's actually given to you down here. Now there's a shortcut to this. An easy way to get the charge of that iron is you simply take the formula, which is this, and you what we call crisscross. You can take the 2, put it behind the iron, take the 1, put it behind the chlorine. I'll just rewrite that. Iron gets the 2. It's a metal, so it's always positive. Chlorine gets a 1, and we always know that chlorine is negative. It's a nonmetal. So you can do this crisscross method to figure out what that charge is. Now if we look at the next one, if I just want to know what the charge of the iron is, I can take that 3 and move it up behind the iron. It's always going to be positive because it's a metal, but we know the value of that charge. So this would be, we would call this iron 3, and that 3 in Roman numerals represents that charge. This 2 represents that +2 charge. All right, if we look at manganese, manganese combined with 4 sulfurs, how do we get the charges here? Well, if you're interested in what the charge of the metal is, to name it, you would take that 4, put it behind the manganese, it would be a +4. This 1 would go over here to sulfur, so -1. But the key here is that you get the charge of that variable charge metal. So we say, okay, it's manganese. What's the charge of manganese? Because it's a variable charge metal, it's a transition metal. Well, it's 4. And then you just name the non-metal with the IDE ending. Okay, so here's an overview of what we talked about. First, you need to be able to distinguish between an ionic compound or molecular compound. If you look at a compound and the only thing in there is nonmetals, it's a molecular compound, and you're going to follow these rules here with the Greek prefixes. If it's ionic, if you see that it has a metal and a non-metal in there, you have to ask yourself, well, is it a group 1 metal, group 2, or aluminum? If the answer is yes, you name the metal, name the non-metal, give it IDE ending. If it's not one of these groups, and it's a variable charge metal, well, you have to figure out that charge. First, you do name the metal just like before, but you have to have those parentheses to tell you what to put, what value to put into the parentheses. All right, and that tells you what the charge of that metal is. Okay, now we're going to discuss something very related because a lot of compounds are made from something called polyatomic anions or cations. Now, poly just means more than one. Atomic means atoms. So polyatomic means more than one atom in the form of an ion. So they're groups. These are basically groups of atoms that stay together and have a charge. Okay. Some examples. Ammonium and hydronium. These are polyatomic cations. Why are they cations? Well, it's a plus sign, so it's cation. There's cation. And this is a group of atoms that stays together. This is a group of atoms that stays together. And so we call these polyatomic cations, and you just need to memorize these. Now we have polyatomic anions. Anions are negatively charged, as you can see here. And they are all polyatomic. There's more than one atom here, there's more than one atom here, more than one atom here, and so forth. The ones you really need to focus on are these three. These are three that you'll see pop up in this course, as well as these. And these are going to be probably the most important. These are also polyatomic anions, but these polyatomic anions can change. And they can change by the number of oxygens that they contain. They'll stay in groups, but they can shed or gain oxygens, and that changes the nomenclature or how we name them a little bit. So first thing you need to do is memorize what we call these representative forms of these ions. This one, we call it chlorate, ClO3 with a -1 charge. These are nitrates, NO3 with a minus charge. CO3 with a 2- charge is carbonate. SO4 with a 2- charge is sulfate, and PO4 with a 3- charge is a phosphate. Okay, so we're actually going to take the representative form of chlorate that has 3 oxygens, so ClO3-, and we're going to take it and see how it can change with respect to the number of oxygens it has. It can gain or lose oxygens, and when it does that, we don't call it chlorate anymore. We have variations of chlorate that we call it, and these are going to be your less common forms, but still are important. So these polyatomic anions, they're polyatomic because there's multiple atoms, and they're anions because the charge is negative. They can differ by their number of oxygens. Let's see how that works for chlorate. Okay, looks like some of my animations are kind of crazy. So here you have chlorate ion. All right, and there's your -1 charge, so you know it's an ion. And there is 1 chlorine and 3 oxygens. Therefore, we call it chlorate, and that's important. That suffix, ate, is going to be important because that's going to change if you take off an oxygen. If you take off an oxygen, we then call that chlorite, a chlorite ion. And if you take off 2 oxygens, we call that a hypochlorite. So we have a representative chlorate, that's our most common form, but it can lose 1 oxygen. When it does, it's no longer chlorate, it's chlorite. Or it can lose 2 oxygens, and we call that hypochlorite ion. All right, so the representative ion that you'll memorize for chlorate, for this ion, is chlorate with the ate suffix, and it has 3 oxygens. If you now see ClO-, the charge doesn't change, but it only has 1 oxygen, you know that's not chlorate anymore. It's lost 2 oxygens, and it's going to be hypochlorite, for example. Okay. Now let's take our chlorate once again, and let's see what happens when we don't lose oxygens, but this can actually gain an oxygen. Now it's not ClO3-, it's ClO4-. We actually call that perchlorate. chlorate ion. All right, so this is your chlorate ion. Ion should be written here. And this is your perchlorate ion. And so in the previous slide, what happened is we took chlorate and we lost 1 oxygen to get chlorite, or lost 2 oxygens to get hypochlorite. Here we're actually gaining 1 from 3 to 4. We call that we keep H, we just add per in front of it. And that means that we took our representative molecule, representative ion chlorate, and we have 1 extra oxygen on there. So it's perchlorate. Now this can happen for any of those representative polyatomic anions on that list, those 5 polyatomic anions a few slides back. I said you had to memorize the representative form. You also need to know the name if you lose 1 or 2 oxygens or gain an oxygen. You're going to use these same prefixes and suffixes to move along that. So if we look at this example, we have potassium, there's our metal. And then we have this, and you should recognize that as one of your polyatomic anions that you have to memorize. And remember, metals are always positively charged. The anions, including polyatomic anions, are negatively charged. And so if we try to figure out what made this, well, it was a potassium ion coming together with one of these. And so if we need to name this particular compound, we're going to say, well, the metal's potassium. So all these examples have potassium as their metal written first, but we need to name that polyatomic anion. Well, to name that, you need to memorize chlorate, and this actually has 2 oxygens taken off of chlorate, so it's hypochlorite. So the answer for this would be potassium hypochlorite. Okay, lastly, we're going to talk about writing formulas from given elements or writing elements from a given compound. Okay, so if you were given a question and the question said something like, a compound was made from, an ionic compound was made from magnesium and nitrogen. What is the formula? Well, what you would do is you would say, well, do I know the charge of magnesium? The answer is yes, I do. It's in group 2, so it's always a +2. Nitrogen is always a -3, so that now I have these 2 ions here. And to write the formula, what you do is take the value of the charge, which is a 2 here, and is a 3 here. You're just basically going to move those down below the opposite element. When you do that, magnesium is going to get this 3, and nitrogen is going to get the 2. And this is how you write the formula from ions. Now, if you were given a formula and you were asked for the ions, and notice this arrow here in the middle is going in this direction, how would you get those ions from a given formula? Well, you just do the opposite, and we've actually talked about this in a previous slide. You take that 2 and you slide it up, you take that 3 and you slide it over there. What that gives you is magnesium now has a 2, and you know magnesium is a metal, so it's positively charged. And nitrogen is going to get that 3, and nitrogen is a non-metal, and so it's almost always going to have a negative charge. And so that is going to be your ions. So this is a crisscross method between ions and subscripts where you can simply just reverse them or put them behind the other element to get what you need. All right, so here, in this first example, we took the charges and moved them down. In this other example, we took the subscripts and moved them up. Here's another example. If I said, hey, what is the formula for a compound, an ionic compound that forms from barium and chlorine? You say, well, barium's in that second column, so it's always a +2. Chlorine always has a -1. I'm going to go ahead and take those values from those charges and put them back below here. Remember, there's an understood 1 there. Okay, so now barium looks like a typo here. So barium is going to get the 1, and then chlorine is going to get a 2 subscript, and we actually never write a 1. There's just an understood 1 behind the barium. Now if I give you barium chloride and ask you what are the ions, you just do the opposite. Take those subscripts and throw them up at the top. When you do that, barium's going to get a 2, chlorine gets a 1, barium's a metal, always positive, chlorine is always a negative. You can also get those from the periodic table directly. So if you have a compound that are fixed, if you have a compound with elements that are fixed charges, you know this is in group, always in group 2, you know this is always in the halogen group, you say, well, just looking at the periodic table, I know this is going to be a +2, this is going to be a -1. So those are pretty simple. So either way works. Look at the periodic table or do the crisscross method. Okay, so let's do some more. We're going to start with ions here and see what the compounds are that form from these ions. Well, if we have a compound that's forming from sodium ion and a chloride ion, what we're going to do is we're actually going to take these values and move them down, a 1 and a 1, to where we have our understood 1 as subscripts. Here we have a 3, the next example. Let's go ahead and move that down. Take this 1, go ahead and move that down. If we do that, you're going to get iron, 1 iron and 3 bromines. Next example, take the 3, move it down, take the 2, move it down, and you get this compound here. Okay, so let's do some more examples. Here's 3. The first one is we have sodium and we have sulfate. So if we want to write a formula for this, we're going to take this 2 and we're going to put it down behind the sodium. We're going to take this understood 1 and we're going to put it back behind the sulfate. When we do that, it looks like this. Now there's only one sulfate group, and so we just simply write SO4. If, for example, if we needed more than one sulfate group, and we had whatever metal is in here, M stands for metal, let's just say a certain metal is going to have 2 sulfates, we write parentheses like this, and we'll see that in just a second. Iron 3 plus and then a bromide ion. This 3 is going to come down, this understood 1 is going to come down to give us this compound here. Now in this next example, we have a 2 that needs to come down behind the phosphate and a 3 that comes back down behind the magnesium. Now there's the 3 behind the magnesium, but how do we put this 2 behind the phosphate? We actually just don't put it here because that's actually 42. What we actually do is we say, well, we have 2 of these groups, so I'm going to put parentheses, and I'm going to put a 2 behind those parentheses. So phosphate is a polyatomic anion. When you have more than one of those groups, you have to represent that with parentheses and then a subscript outside the parentheses. And this basically is telling you that there are 2 of those groups. Okay, so now let's take some formulas and ask what are the ions formed from these formulas. And so to do that, you take the subscripts, which is a 2 for chlorine and a 1 for iron, and we're actually going to move those up to give us charges. So this is going to be an iron 2 plus. All right, there's the 2 we moved up from chlorine. Iron gets it now. Iron is a metal, so it's a plus always. And there's chlorine's understood. When we see that minus sign, it's a -1, understood -1. If we look at the next one, potassium chloride, there is going to be an understood 1 for each one of those. When we don't write a subscript after an element, it's understood that it's just 1. You know, if we take those and we move them up, move that one up, move that one up, we're going to get these ions. Why is potassium positive? Because it's a metal. Why is chlorine a negative? Well, it's a non-metal. If we look at the next example with 1 calcium And one sulfate, we know it's one sulfate because if it was two sulfates, it would have parentheses around it saying there's two of those. But we don't have that situation. Well, if you look at this one, you know from the periodic table, for example, that calcium's in group 2, so calcium's going to get a 2 plus, and sulfate, which you'll memorize in your polyatomic anions, is always a -2. So let's look at this next example. Here we have iron sulfate. So which one of these irons, what does iron look like? That's really the tricky part here. We know SO4 is a sulfate, that's a 2-, that's the ion that came together to form this. And the question is, well, if that's the case, what is iron's charge when it came in to form this compound? Remember, compounds always have a no charge, 0. So everything that comes in to form this has to cancel out. Well, if sulfate comes in with a -2 charge, seen here, and so we have basically a -2 for sulfate, and those need to equal 0. What does that mean about iron? Well, that means that iron had a +2, because if you have a +2 combined with a -2, you get 0. So our iron is going to be a 2+. That does not look like a 2+. Here we go. I'll write it. Nope. Write it correctly. 2+, and then 2. And so if we need to name this compound, we know a 2+ iron came in to form this. So we're going to say iron 2, because it's variable charged metal, we have to put the which cation came in, which iron came in to form this. It was an iron 2, and then we're just going to name whatever the polyatomic anion is. So that'd be sulfate. So it should be iron 2 sulfate, which is this.